Let's get started. Welcome everybody to another NLP with Friends. We're super stoked to have Sabrina Mielke here for the first talk in September. She is now a fourth year PhD student as of yesterday, or Monday, I suppose, at Hopkins, largely working on open vocabulary language modeling and with a whole host of other cool side projects. And so as a reminder, we're going to collect questions on Dory. This will be recorded and we will post it later, but we will not record the question portion. So you should feel free to ask whatever it is that you like. And with that, I'm going to turn it over to Sabrina.
Awesome. Yeah, thanks. And thanks for inviting me. And thanks to people for showing up. This is great. Yeah, I'm going to talk a little bit about some stuff that I've done in the past and some stuff that I'm working on right now. Most of this talk, unsurprisingly, is basically conference slides. But I spent some time last night scribbling some new things in there. So maybe, hopefully it'll be a little bit more entertaining. We'll see. So yeah, if you have any questions that really pertain to what I'm talking about right now, please do feel free to just ask them, raise your hand, put them in the Zoom chat or Dory, and then hopefully we'll manage that. So I think that'll be better than just asking everything at the end. But yeah, let's go. First of all, since I'm going to be talking about language modeling throughout this talk, I thought it was important that we actually settle on what this means, just so we're on the same page. So language modeling in NLP is a generative story of text. We want to have a generative model that is basically just a probability distribution over text. So if we have this really amazing short sentence that's not even grammatical, but whatever, the cat chased the, you can imagine it goes on. Usually it's decomposed into being generated, say, word by word. And so this is a valid decomposition. We start with the first word, then the second conditioned on the first, the third conditioned on the previous ones, and so on. And this is so far in exact decomposition. We didn't lose anything. Now, if you're like older than, I don't really know, but if you do n-gram models, you would then, strike these things out, blah, 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 blah. But since we're all doing RNNs, we're not really doing RNNs even more. We're doing transformers now. Anyway, since we're doing models with a lot more context, we can keep these things in there. Specifically, so if we take like an RNN model, we would have these, basically a vocabulary. It's got a bunch of entries in there. They have their spellings and they have embeddings. And so, well, we are now going to use them in an RNN cell, do a softmax over all the output embeddings, sample a word, feed it back in, sample the next word, and so on. And so that allows us to get this probability distribution over text. Great. But what happens when we encounter a new word? So that's where the open vocabulary part comes in. Open vocabulary means that we assign probability even to new words. We don't have to anything, right? Because that's the standard thing people might do, say, okay, well, we have another type in our vocabulary that's called unk. And we're just gonna predict that, and we don't have to predict that it is caged. We can just do unk, and that's fine. And you might already, the way I'm making it sound is on purpose. I think this is cheating. I think this is boring. And we are later going to explicitly require that no, we need to spell this out. We need to tell what is the word. So as a solution, just to quickly show the thing that everybody's thinking about, probably you could do a pure character level model. Okay, sure. So now we do character by character, and then it's not hard to do CAGED as a new word. But character models kind of suck because now I have to spell THE space, and it's like, can't I just memorize this? Yeah. So since it is now 3 years after I started this project, you're going to be like, yeah, you just use word pieces or BPE. And you're right. But at the time, people, for some reason, weren't doing that. Language modeling was weird. Anyway, so with that background, let's talk about what I'm going to do to these language models in this talk. First, we're going to talk a little bit about evaluating them on different kinds of languages and trying to draw interesting conclusions. Then we're going to extend that methodology to translation models and kind of talk a little bit about what information might mean in translation and what it really is that we want to measure. And then I'm going to briefly go over two other papers. One where we built a new language model, and there's going to be some interesting takeaways there, and one where we look at bias in language models, in gender stereotype bias specifically, which has some interesting tidbits in there. So yeah, that's going to be roughly the shape of this presentation, starting with evaluating language models. So what we want to do in this paper is basically answer a few questions. The first question we might ask is, okay, well, do language models do equally well in all languages? And the answer there is no. They work better on some languages. The ones that we have these days work better on some languages than on others. We can then say, okay, well, what kind of language is kind of hard? You know, like, is German harder or English harder, for example? And the answer there is German. Now, these two questions are not really questions that we answered in this particular paper. This is stuff that we answered in the paper the year before in a very preliminary short paper. It's like one of my first projects as a PhD student. It was very exciting. And so this paper says, okay, well, let's try and do something more complicated and more languages and more data and more careful. Because I was like, oh, well, we had this successful paper last year. I'm just going to do a little extension, and it's going to be a publishable paper, no work at all. It's awesome. I'm just going to do this. If only it had been this way. But anyway, we're going to ask some different questions. So we extended this to non-Indo-European languages, say Chinese. And the answer there is it kind of depends. And we're going to see what that is. Thanks for the question. Yeah, what do I mean by harder? That is something we're going to get to in a second. Because that's kind of interesting to define. That's really where the bulk of the previous paper, the contribution of the previous paper was. So yeah, what makes the language harder to model is not quite that question then, but is there any linguistic correlates or any properties of the language that make it hard for a language model? And it turns out, well, no, not really, but there's some really boring answers. And finally, the one that I actually am most excited about in this paper, we looked at whether Translationese is easier or harder to model. And the answer might surprise you. We're going to get to that later. So that's the outline of this little section. We're going to define difficulty. We're going to talk about what models and languages we used, and then see if we find these correlates with difficulty, and finally look at Translationese. So how do we measure difficulty? Now, language models, since they are probabilistic models of text, give us the probability of any string. We can take the negative log, and that's the negative log likelihood. Sometimes also just called the surprisal, which I think is a nice way to put it. So that's really what we want to look at. We want to look at how surprised is the language model when it sees text in that language, right? So if it's very, very surprised, then chances are it was a bad language model because that's what text in that language looks like. And if it's not surprised at all, if it really anticipated this, great. Surprisal then is measured in bits. And yeah, this does correspond to like imagining you wanted to compress the text. And so again, the more you can compress, the lower the bits, the lower the surprisal, the better. Okay, so we might look at an English sentence here. We'll take a German sentence and we'll take a Dutch sentence. And, okay, well, that's obviously garbage because these sentences are just not comparable at all. Like the first sentence has 5 bits only because it is much shorter than the Dutch sentence. So we really need to, first of all, make sure that we don't have these different topics, styles, and content. And so what we do is we do all of this work on translations. So if you're familiar with translation, you probably know Europarl. It's like this well, I don't say too old, but definitely a corpus that has been used a lot, for better or worse. 21 European languages It's transcriptions of the European Parliament discussions, and they're not all present in all 21 languages, but you can, get a reasonably large subset in 21 languages. So this is 40 million characters, which is decent. Just as a fun note, if you work with Europarl, you probably have seen this sentence quite a lot. It's everywhere. Classic. Yeah, exactly. What we also did in this work is look at Bibles, because we were like, okay, well, we want some non-European languages. We want some more languages. And so Bibles felt like the best way to go at this, the best way to really get translations in as many languages as possible. And you might say, well, why 62 languages? There's like hundreds of Bible languages, right? No. Most of the Bibles that are out there are just New Testaments, which is like, okay, that's nice, but it's not really the whole Bible. And so we really want like as much as possible. 4 million characters is already quite little, to train a big neural language model. So overall, okay, 62, then how do we get this? This is actually super fun, and it was one of my most fun parts, my most favorite parts of this paper, solving the interlinear program that gives us this answer, because not all Bibles share all verses. So now you have to select some verses that are shared by as many languages as possible. So it becomes this crazy optimization problem. You plug it into Gurobi, and a few hours later it says, use these 62 languages for maximum, whatever you want. Great fun. You can check out the paper. So we end up with 69 languages. This was not on purpose, but it's still nice. Issue number 2 that we're going to have to talk about is, how do we compare these scores? And the answer there is, we want to use the total bits of an open vocabulary model. Okay, now why? We need to be open vocabulary, no unks. As I said in the beginning, unks are kind of cheating. And this is particularly bad if you have like a morphologically rich language. Our language just has many word types, because morphology creates lots of them. If I say, oh, I only take the 10,000 most common types, in a language like Turkish, that's not going to get me far. So I'm going to have lots of unks. So Turkish is going to look easy because there's unks. So no unks, we need to be open vocabulary. And the second thing is, we can't look at perplexity per se. That is, perplexity is basically taking the overall surprisal and dividing by the number of words. So we get a measure for like how surprising each word is. Now, if you stay within the same language, that might be reasonable, but we can't do it across languages, right? Because if we imagine this hypothetical language that is spelled without spaces, well, that's going to be very surprising for a single word. Whereas in English, where like words are kind of small and kind of, they don't carry as much information, that's going to look easy. So that's not going to fly. We need to be total bits. Now, there's an interesting side note, because people asked about this. Can we use phonology? That might be an option. We didn't look into this, but that might be an interesting option. Then another thing you might say is, okay, well, you can't do words, but characters kind of work out, right? And there's this neat little example here that's like putsch, which is the word for coup. It's basically the same in Czech and German. But since the Czech one only uses 3 characters, that's going to look a lot more difficult for a character, even though, it's not much is happening there. So overall bits of an aligned sentence in an open vocab model. That's what we're going to measure. We can easily obtain this. Like if you have a model that only gives you perplexity, yeah, just multiply, take the log and multiply with a number of words. So what does our model then look like? What do we do with these things? So what we've talked about right now is how we go from this matrix of text, different languages and different aligned sentences, to surprisals, to these total bits. And so this is kind of supposed to show, like darker colors are more difficult, something like that. So if we look at this matrix, we can already see that, German is probably harder than the other 2. English might be a little harder than Bulgarian. It's kind of hard to make out. It's kind of funny. Sentence 3 is probably like a really, really long sentence. That's why it's so hard. And sentence 1 is just resumption of the session. So that's really easy. So we can kind of do these things, right? And so what we did in the previous paper then was, just add them up or average them, whatever you want to call it. I mean, it's the same thing. And then we get these scores for languages and we can compare them, and great. Sorry, the number on the y-axis is just which sentence in the corpus it is. So each row is an aligned sentence, triple in this case. But what if there's missing data? Well, now we can't average anymore, right? So you might say, okay, but there isn't missing data. You selected it to not be missing. But bear with me. This will come in handy. Let's just imagine for now that there was missing data. Then what will we do? We can't average anymore, right? Because now if we average, German and Bulgarian look really, really hard. And English looks really easy just because it skipped sentence 3. So what we introduce in this work is a fully probabilistic model for these surprisals that gives us estimations of difficulties of languages. Specifically, what we're going to be saying is that the surprisal of a sentence in a language is the product of the sentence difficulty or sentence complexity, which really is sentence length, more or less, with the difficulty of the language. So this is a pretty standard mixed effects model, really. And this product thing kind of stems from the idea that we think that the difficulty is like, the bits per unit, and then n is how many units are in a sentence, something like that. And now we can put priors on these things, have probabilistic noises, and it's great, and we can go totally overboard. And go overboard is what we did, because our actual model becomes even crazier. So this is our actual model is heteroscedastic, which was a word I had never heard before this paper. But now I see it pop up everywhere. It's like very funny. Once you know these things, like see them, and you're like, oh, I remember this. This is the thing that my advisor made me do. What is heteroscedasticity? So that's what my newly added slides look like. They're kind of sketched. I'm sorry if you can't read it, but that's okay. I'll read it out. So heteroscedasticity really is this idea that that the variance is not constant. That the variance of the noise term is not constant. So what do I mean by variance of the noise term? Here, if we say that the surprisal is the product of sentence complexity and language complexity, well, it's going to be somewhere close to that product, right? And the loss that we have, the distribution over where these surprisals may lie, is centered, okay, it may be centered at this product, but it's going to have some variance. And the observation here is that the variance of longer sentences is actually smaller, because longer sentences have more individual units, so that overall it kind of evens out and you come very close to the correct estimate. Whereas a short sentence like resumption of the session, well, that's going to be like, you don't really know. It could be very far away from your product estimate. So that's what heteroscedasticity is all about. Great. So we get heteroscedasticity, we get Bayesianism, and we can put good priors on things, and do some checks and all that. Now, since this is a really crazy Bayesian model, I was like, okay, well, this is not conjugate or any of that stuff. But we have these cool tools that can do Hamiltonian Monte Carlo, which is super fancy gradient-based MCMC, basically. So if you know MCMC, you know that it's kind of slow and nasty. But it turns out you can make it a lot faster and more efficient if you have a model that has gradients. So that's what Hamiltonian Monte Carlo is. And if you look these days, like it's become very popular in machine learning to use stochastic gradient large-model dynamics. That's basically HMC simplified. So yeah, it's definitely a thing people like to do. So I coded this up in Stan, which is really funny because it's a very interesting toolkit. It took like a few weeks because it was unstable, and then it took a few more weeks to really see what's happening and check some priors. And as an individual run would take hours to get a few samples because it was really a nasty specified model. And in the end, misery. It makes no difference whatsoever. So this is saying that for the full data case, so if you don't have missing data, doing all this fancy modeling with its heteroscedasticity and noise terms and Bayesianism and priors and Hamiltonian Monte Carlo and all that stuff came out to basically the same as averaging, and basically the same means we had a Pearson correlation of 0.999. The moment I saw that, after having wasted half a year on getting this fucking HMC to work, I was very mad that day, and I made sure to let my advisor know. I didn't appreciate that he made me do this, but I learned a lot, so now it's good. Also, this is just I'm very proud of that slide. Anyway, so that's the story of how I wasted half a year doing crazy complicated things that were absolutely useless. But it wasn't quite useless, and that's what we're going to get to in the end. For now, let's continue with the standard story. We tested some vocabulary models. We have a character level model. We have a BPE level model. We have another BPE level model. And you might say, what's the difference? The difference is that we can control with BPE the number of merges, and that kind of lets us interpolate between a word level model and a character level model. So we were like checking, okay, well, what's the right thing for different languages? So here what you're seeing on the x-axis is how many merges do we have, where merges are given as how much percent of the total vocabulary size in our training data is getting merges. So that's not quite the same as numbers. And in fact, I'm going to, in the end, talk about why that might have been a huge mistake. But what you can see in this plot that shows the surprisals, so lower is better, is that it really depends on the language, which one is best. So you see that Hungarian really wants to have not too many merges. If I give Hungarian too many merges, it becomes worse, which kind of makes sense in the sense that like it has a lot of morphology going on. So splitting might really be a good thing to do, a good inductive bias, if you want to call it that. On the other hand, English all the way down, it's that lowest black line. We can basically go all the way to merging as much as possible, and we just keep getting better because the words are kind of independent, standing on their own. So that's really interesting. So you might say, oh, wow, so now you have to tune every individual language. We were kind of like, yeah, we're not going to do that. We're just going to take the average of all these, and then 0.4 is probably going to be fine-ish. But since both my advisor and me are perfectionists to a fault, we were like, but is it actually fine? And so we checked that it doesn't matter, and it really doesn't matter all that much. So what you see here is again what you see here is a difficulty language estimation. Difficulty estimation. You might as well say that it's still the surprisal of 3 different models: BPE when using the best for each individual language, BPE when using 40% for all languages, and the character level model. And so you see there are differences between the 40% model and the best for each language model, but they are really not that great, especially if you compare them to the character level model. So we went with 40% for all our experiments, especially on all the other languages. So now, time for results. We can kind of build up this graph that has on the x-axis the difficulty using BPE, and on the y-axis, the difficulty using characters. So all the points should kind of fall somewhere along these lines. If they are far away from the line, that means that they are much either easier with BPE or easier with characters. So the Europarl languages do kind of follow this line. What we can see in response to the question in the beginning, German is harder than English under both models, although this difference is more pronounced with the character level model. So that's Europarl, which is nice, but now we want to look at the Bibles. And what's really cool about the Bibles, the line drawn is just the identity. So that's really saying that the difficulty under both models should be the same. So now we can look at the Bibles, and what's cool there is that we have multiple English and multiple German translations. So we get kind of an estimate of the variance and see like how much of what we're estimating, what we're measuring is the language, and how much is that particular translator's just style, and how much is that particular, just particular random instantiation. And we see that there's a whole lot of noise. That is true. But even so, the trend that German is harder than English is very much clear. Yeah, to explain what is difficulty here, because it is this weird numbers. The difficulty here is this factor in our model. So in the model, we had the exponent of this number times units per sentence, which is kind of like, it's not really clear what that means other than that it is basically a logarithmic scaling factor. Yeah. So sorry, that's not really all that interesting, I guess. But that's how we did it. It's actually really interesting. We could talk about like, why do we need to plot the logarithmic one as opposed to the linear one? And there's a good reason for that. But yeah. Okay. So that's nice. And we could put in all the other Bible languages, and we see that the correspondence between difficulties on Europarl and difficulties on the Bibles, that's what this middle plot shows, are not perfect, but they're decent. So like German and Hungarian are hard, English and Lithuanian are easy, plus minus. Sorry, you can be this conversation. Yeah, you're right. This is the score as estimated by that fancy probabilistic model, which for now we can still assume that it's basically just the total surprisal of the entire test corpus. Yeah. Okay. So also answering the question of Chinese, that was really cute. Chinese is kind of hard for BPE, but easy for character level language model, which makes sense because it doesn't work that way, right? Characters are already like a very good unit to be modeling Chinese in. Yeah, so we got that talked about. So now let's look at, what might be interesting, what correlates with these difficulties. So here's a plot that's like, we were like, okay, well, maybe morphology makes a language hard. So we put all the languages on these plots. The x-axis is a measure for morphological complexity, very simply just counting all the different inflections that exist. So you see Czech and Finnish have a lot, English has almost none. And then the difficulty on the y-axis. Basically the same Czech and German. But since the Czech one only uses 3 characters, that's going to look a lot more difficult for character. Even though, Sorry, is there an echo?
I think that was an echo. Okay,
well, I'm just going to keep going. So yeah, I don't know about you, but when I look at this, I do not see a correlation, which is interesting because in the previous paper the year before, we claimed that this was a great correlation. So what had happened there? We had some different things, and especially Finnish was different. But the moment I compared these, this was a really fun conversation. I was like, hey, author on our previous paper that ran the experiments, my numbers don't match yours. Ours. Okay, yes, ours. Well, I was on that paper. And I was like, okay, well, can you give me the code? What code did you run to do this? And the answer was like, yeah, well, I took some language model. I don't know. I don't remember. So that was great. So we can reproduce it. Beautiful. This is all reproducible, luckily, that whole paper. But that was a whole mess. So we were like, great. Okay, well, good start for this paper. Good start. So we might say, okay, maybe it's not morphology. Maybe there's some other things that correlate. We can look at Wall's features, like another morphology feature. Nope, nothing. SOV order. Nope, nothing. Some things that people have proposed, like the entropy of heads of proto-speech tags. Nope, nothing. Average dependency length, which people have hypothesized is responsible for some difficulty. And yes, we did see correlation, but correcting for multiple hypotheses, because we tested lost off correlations, right? We have to correct for that with like Bonferroni or Benjamini Hochberg. The correlation is no longer significant. So I'm going to call that a maybe. Maybe might be worth checking out. But overall, this is disappointing. So that was another conversation we had. I was like, hey, professors on our paper. So nothing interesting correlates. We got a lot of negative results. What do we do? And I was like, okay, well, this will be tricky, but we're going to have to just attack ourselves. And so that is how we positioned the paper then, saying like, look, these previous authors, kind of the morphology thing, it doesn't really work. It's not reproducible. Here's our great new, much more sophisticated method. Shame on this previous paper. We submitted it. It got rejected. We submitted it again. It got accepted. And then we kind of, evened out the writing a bit and be like, well, we can't reproduce our own numbers, but it's fine. It happens, you know. Yeah. Anyway, we did find something, however, that correlates, and that is these what I call very simple technical heuristics. So for the character level language model, the raw sequence length is significantly predicting difficulty. And what do I mean by raw sequence length? I really mean how many characters there are in the test corpus. The more characters there are, the more steps I have to take, the more individual predictions I have to take, the harder the language then appears to be, which is really interesting because I believe the reason for that is just the fact that softmax is leaking probability everywhere and you can never be 100% certain. So that's really fascinating. And maybe, you could do this with like different things. Maybe you could do it with sparsity. Maybe you could do like mixture of softmaxes to get a little more power in your softmax. But I thought that was really cool. And the other one is BPE-RNNLM's difficulty is also very easily predicted, at least on Bibles, by languages that have a large vocabulary to begin with, or large type token ratio, whatever you want to say. They correlate very strongly. So that I thought was really interesting. I was like, shouldn't BPE take care of that? That is so weird. What is happening here? We have many conjectures I wrote on the slides. And then when I presented this at ACL, I was literally standing up there talking about it. And just at that moment, I realized I really might have messed something up. I think the issue here is that we took the 40% BPE merges, and of course 40% BPE merges preserve how large the vocabulary was to begin with. Of course that information is still in there. I mean, where the hell should it have gone? So yeah, take that one with a grain of salt. It was just great. Anyway, at least I hope nobody noticed me falter during the talk. So that done, that's kind of the first 2/3 of the paper. The interesting bit comes with Translationese. And now finally, we're going to get to use our fancy model. Thank God. The common assumption now in the literature is that Translationese is like easier than native text, be it because translators have like this additional overhead and so they stay simple, or maybe it's like it's produced in like a different context. It's kind of unclear, but people generally assume this, so you can find citations for this. And now the neat thing is with Europarl, we do have parallel data that indicates whether it's an original or it's a translation. So every sentence, every row in our corpus is original in just one language and translated in all the others. So now we have this matrix, and you might say, yes, this looks exactly like the missing data matrix we were talking about at the beginning. So what we can do is, well, model all the things in this matrix. That is, train a language model for each language in this matrix, and then test it on the test set. Test it on the test set of each language in this matrix. And that should give us difficulties for all of the now 42 languages, 21 original ones and 21 translated ones. So if we do that, we find out, yeah, the original languages are harder. They have a higher difficulty. So is this all? Well, no, we missed something. We missed something very crucial. And luckily we found this before submitting. We trained mostly on Translationese, right? If we train on this matrix, if we train the models on these things, they're going to be trained mostly on Translationese, because even in the language that has the most native sentence, English, you have less than 20% native sentences, and the others have even less native sentences. So it's really, really, the model really doesn't see a lot of Translationese during training. And so it's not that weird that Translationese has higher surprisal at test time. So I believe that this only shows that Translationese is different. It doesn't show that it's easier. So now we can go the extra mile, and this is the final experiment of this paper. We change the training set, and we make sure that when training, we train the models on as much original as we have Translationese. So in this case, we can only ever do this to a single language at a time, right? Because otherwise the constraints don't add up. So say we're splitting English. Then in this case, we had 2 original English sentences and 1 translated. We just delete one of the originals from our training data so that we have as many original as translated. Retrain our models, reevaluate our models on the test sets, and look here. difficulties are now the same. More precisely, you know, it's like a little bit easier, but there's so much variance. No, it's practically the same. So that's really fascinating. I was like, whoa, this is something people have not seen before. And I think this is something that might have gone wrong in a lot of previous experiments. Translationese is different, but it's not more difficult. So I thought this was fascinating. Now I should say, I'm not making linguistic claims here. There are certainly, you might certainly say that in terms of like use of syntax or use of vocabulary, you could be very fine-grained and say, well, in this axis, Translationese is easier or something like that. Those are very well good statements, and we cannot tease those apart with our models, right? We don't really know why it's easier or harder. But we can say that current day language models do not find Translationese easier. So yeah, that was that paper. Make sure your training data is comparable and fair. Make sure your metrics are comparable and fair. Make sure your stats are fair. No p-hacking, please. Always do Bonferroni or Benjamini Hochberg. And work on more NLP resources for more languages, because Bibles kind of suck. This is still like one of my favorite papers that I've written. It was basically this thing that was supposed to be, oh, this is very easy. I'm just going to add some more languages, and then we're going to have a follow-up, and I'm going to get a free ACL paper. Dope. And it turned out to be this 1.5-year endeavor, learning all about probabilistic modeling and figuring out all these things. You know, that's how that goes if you want to have an interesting paper. And I think it turned out interesting enough. So I'm going to give you, and I'm going to have to speed up a little bit, I fear. I'm going to give you a little look at what we did to translation models. So with translation models, you could also say, like, how can we compare them? Y'all, or like people who do MT, have probably seen this BLEU website that shows all these scores between languages, all these BLEU scores. And you might say, like, are these comparable? Well, not really. BLEU kind of sucks for comparability. It also sucks for other things, but it also sucks for comparability. The reason there is similar to why Perplexity sucks. It's that tokenization works different across languages. The meaning of a word is different across languages. And so having matching 1, 2, 3, and 4 grams doesn't mean the same in all languages, right? So we can have, I will have been programming in English, that can be a single word in Turkish. And so getting that 1 gram right in Turkish is going to be harder than getting 1 gram right in English. So translating into a different language, you cannot compare BLEU scores. Now you can compare BLEU scores translating from different languages into the same language. That's possible, but that's not all we want to do. We want to go both ways, right? So what we're doing is, again, use this idea of looking at the likelihood, that is looking at the surprisal under a current day translation model. But even that still combines the difficulty of translation and the difficulty of generation. And that's really an interesting point here. That's I think the main contribution of this paper, not so much the results, they're kind of useless, but asking this question, what do we mean by difficulty of translation? We can take this very downstream view and say, well, BLEU score matters because BLEU score is kind of like sort of correlated with how useful or good it looks to humans. That's fair to say. We could also look at this likelihood of the target. But if we look at the likelihood of the target, I believe we are conflating these two things. Because to generate the target, you need to both understand the source and draw some things from it, transfer them into the target language, and then produce grammatical output in the target language. And we've seen in the previous talk that that is not working equally well for all languages. And so in this paper, we are teasing those two apart. We are asking how difficult is not the entire process of translation, but how difficult is just this reading and extracting without the generation part. So what does that look like? Okay, well, we've talked about this, so I'm going to skip through this briefly. We know what the surprisal is. The entropy is the average surprisal. That's all good. We have conditional and joint distributions. We've seen those, Bayes rule. We can do our definitions for these too. And so now we come to the information theory bit. I'm sorry for advertising it so much. I just liked my pun. But it's really a very simple concept that we're using here. And that is the concept of mutual information. Mutual information measures how much is shared between two random variables. And in our case, these random variables will be a source sentence and a target sentence. So what is mutual information? We start with the uncertainty we have about Y, about the target, a priori. And this is really just the language modeling, right? This is what we've seen in the previous paper. And we subtract how much uncertainty is left in the target, knowing X. So if we know the source sentence, how uncertain are we still about the target? How surprised are we still that the target turned out to be that particular translation? So it should be clear to us that the first term is bigger than the second term, right? If we don't know the source sentence, we have no idea what the target's going to be. But if we know the source sentence, we have some idea what the target is going to be. And that reduction from no idea to some idea, that is mutual information between the two. So this is symmetric. It goes both ways. So this is really a measure of sharing. And this is what it might look like in a picture. You know, we have the source sentence, we have the target sentence, and they both entropies decompose into from the full one into like just subtracting this orange block. That is, you know, how much uncertainty is left after translation. And then this blue block is the mutual information that we're looking for. So there's an issue here. This assumes that we have good probability distributions, and we don't. We have models. So we say we take this idea of cross entropy and apply it to mutual information to come up with this thing that we call cross mutual information, or XMI. And cross mutual information looks like mutual information in that we still take the entropy that we only have of the target sentence, that we call here QLM, which is estimated by a language model like in the previous talk, minus the entropy that we have using an MT model. That is, you know, entropy over the sentence, over the target sentence, given source. And so it's, you know, still kind of a measure of mutual information, but not quite. Now this has some not so nice properties. It is no longer symmetric because training an MT model in this direction is different from this direction. But it still is an interesting thing to look at, we say. Now there's an interesting thing. If you look at this picture, does anyone take offense at that picture? Okay, well, at some point we were like having lots of conversations about this. It's really funny, like the paper got accepted, and then after we were like, you know, actually, I don't think this math looks right. Let's change this up a bit. So the cross mutual information we actually only came up with after it was accepted. Before it did some weird normalized thing that I don't know why, and so we went in and fixed that and made it nicer. But anyway, I made this picture and like we discussed about it a bit, and it was like, is that really correct? You know, and I was like, yes, my pictures are perfection. I'm always right. Obviously, like who isn't always right, right? And you know, some back and forth, and eventually people were like, yeah, no, that makes sense. Cool. The paper was published. The paper was advertised. People read it. And, you know, I made slides for this, for some talk I was going to give. And then Emanuele made his slides. And he's like, you know, actually, now that I'm thinking about this, is that picture correct? And he says, like, shouldn't it just add up? Yeah, it should. So I was like, yeah, no, you're right. It should. In this previous picture, going back, even here, I have these like kind of wobbly, but the way we define XMI is still the difference between the two. So it shouldn't be this wobbly. Damn, but nobody noticed. It was infuriating. So the paper is still out there like that. We still haven't decided what to do with it. But yeah, oops, no, lol. Why did no one tell me? Yeah, one of the many embarrassing moments of my career. Good times. So we did this on like a few languages, English into language, and language into English on Europarl again. We can see that from a language into English, BLEU correlates well with XMI, which is good because that was the case where BLEU was comparable. Sorry, what I meant by wobbly is that they don't add up anymore. So that's great. And then if we go from English into other languages, we see that BLEU and XMI don't correlate as well anymore. And this shows that indeed, while XMI is comparable, BLEU really, really varies. And so we argue that XMI is the thing to look at. Now, there's a ton more correlations in the paper if you want to look at those. But yeah, we can also look at this per language. I'm going to skip through this. The high-level takeaway here is that for all the things that we tested, it was easier to translate out of English into a foreign language then it was to translate into English from a foreign language. Now, this might be because our definition of easier explicitly subtracts the difficulty of generation. And we've seen in the previous paper that other languages are kind of hard to generate. But I thought this was a really interesting takeaway. So that's why, like, it really depends on what you're trying to measure. Are you measuring like the whole process, including generation, or are you not? And so that's really what this paper is about, I think, asking these questions. We also made like a table. It was like, hey, does it correlate with linguistic thingies? Déjà vu, nope, it doesn't. Which again was really frustrating. And we're gonna get this TTR correlation. Yeah, what a mess. We probably at some point, hopefully, might scale this up to more languages and evaluate more pairs. Let me know if you're interested in doing something on that. We can try to use better models. So these have limited amount of tuning. This was Emanuele's project before he even started his PhD, which is really impressive. He's a really cool researcher, and you should check out what he's doing. Yeah. So now, should you use this in your system? Should you report it in the papers? No, I don't think so. But you should think about the concept. If you really want to ask this question, what it means to translate and what it means to be easy or hard, what it means to have performance, I think that is a good and useful thing to think about. Speaking of performance, since I felt bad having a whole talk just analyzing things and not showing off my big NLP engineering muscles, or whatever this is, I did want to have one paper where we actually build a model, and that's this paper that I stole the slides from in the beginning. And this was my first paper when I started my PhD. I was like, okay, we're gonna do this cool language modeling. Awesome. I read all about this. I read all these papers. I'm just gonna build my own LSTM language model. So this is September. So I built a language model. It had pretty awful complexity. So this should go down to like 60, 70 state of the art. It's like, oof, this was pretty bad. Time to really go into the literature and figure out what the tricks and hacks are to make this better. And I did that. And I got to like 100. I was like, okay, October, I was still at 100. And I was like, November, I was like, okay, fuck it. I'm just going to clone the awesome Salesforce LSTM-LM and start my experiments on that one. And voila, we got great complexity and we built a state-of-the-art model. So what does that model look like? The idea here is that we really want to look at this relation between spellings and meanings of words. I'm going to get into that a little bit later. But the model itself is very simple. We form it as a generative process, again, where the embedding of a word informs its spelling. That is, we have a character level RNN that tries to generate the spelling of a word given its embedding. And when I say tries to, I really mean that this is a training loss that we add. So this is how we connect embedding and spelling. You could say it's a regularizer that regularizes embeddings to be predictive of the corresponding spelling. So like now our embeddings become more spelling aware. Okay, that's nice. I don't really see the point yet. We're going to do this. Now we get these embeddings and spellings. Great. And now we can generate text. Standard RNN procedure. We have our RNN hidden state. We look at the embeddings, sample one, and then, print out the spelling of that word on the screen. We feed the embedding back in, next word, printing, next word, printing, next word, printing. Okay, that's how you generate text or, have a probability distribution over text. Standard language model. The interesting part is, what do we do in this case where we have a novel word that is not in our vocabulary? And so we're using a little bit of a trick here. We are introducing a new UNC token, a new UNC type that we can predict here. And we can say, oh, this is going to be novel. But we don't give up there. And that is the difference between a closed vocabulary and open vocab model. We are still open vocab because now we go and spell that word out using the model that we've trained to predict spellings from embeddings. So we have this RNN cell, this character RNN model that is used both for in-vocabulary words and for the novel words. And it turns out that using both for training is crucial. And so we get this nice synergy between them. And this helps us be a great open vocab language models. This is some samples from the model. You can see that the things that are in typewriter font, those are novel words generated using this mechanism. And you can see, it makes perfect sense and it's really appropriate in context. We got a year, it looks like an organization, looks like a place name. It was really cool that it really picked up on these things and did them nicely. Now I know 3 years later, or I guess 2 years later, people really don't care about these things anymore because we got GPT-3. But at the time, I was very, very amazed by this. We can also do a more fun experiment. That is, we can take words that are in vocabulary, so we know their spelling, and then sample a new spelling given our character level RNN from this embedding. And so we end up with this new spellings. And you can see that while the meaningless part of sorts, lemma, changes, the morphological stuff doesn't change. So the first thing stays a past tense verb. The proper names still look like proper names. My favorite one is actually chance turning into tranquil. So that maybe I'm seeing things, but that looks like some semantic transfer even. I was really amazed by this. Now, this is the slide as I presented it at the conference. I didn't cherry pick these examples. I sampled 8 examples from the model, but I deleted the 8th one. But I'm going to show you the 8th one, and you will see why I deleted it. Now, this is literally not cherry picked. The model literally turned Minsky into shite, period. But I figured we couldn't print this in the paper. No one was going to believe us that this really happened, right? This is insane. But, you know, I put it in here because the fuck. Yeah, so why is this a good way of modeling language? Let's talk a little bit about the background of this. The question that we're asking here is, how should a word's embedding and its spelling be connected? And so, you know, if you do like standard, you know, linguistics you learn in high school, it's like, oh, the sign is arbitrary. That is, the connection between spelling and meaning is kind of arbitrary. Now, this does not mean morphology doesn't exist. It really is more about the lemmata, right? There's no reason apple is called apple. And yes, onomatopoeia exists, but, you know, basically. We extend this into a central tenet of our model, that is, meaning is not fully predictable from spellings. That is, the correspondence between embedding and spelling is not perfect. There is a signal there, but it's not perfect, right? So you might have these cases like silly and folly that end in ly but are not adverbs. And so our hypothesis was, if we do what just about everybody else does, that is, construct word embeddings from characters using like a CNN or whatever, we fail on this because this construction model sees ly and says adverb, which is not true. So it has to learn all these different exceptions to really work well. Our model doesn't. Our model is fine saying, whoa, this embedding doesn't look like a silly because it shouldn't end in ly. But that is just one lost term out of many. So in our thing, we allow pairings a priori and just use it as regularization. So outliers may have idiosyncratic embeddings. The tenet here is regularize embeddings. Don't construct them. Why do it this way then? Well, so there's another access to this. Why do it on the type level, not on the token level? We really want to make sure that function words like the and of that have incredibly uncommon spellings, right? If you look at like an English corpus, try to look at the bigram space th. There are tons and tons of tokens that start like this, but a very, very small number of types. In fact, all these things that start with th, or pretty much all of them, are closed vocab things, are things that we certainly have seen. So if you have a novel word, it almost never starts with th. So if we train our character level model to be really good at making th into something useful, that is absolutely wasted because we do not need it. And that is why we do the training of the combination of embeddings and spellings on this lexicon level, as opposed to in running text on tokens. And this low cell. So yeah, I came up with this neat thing that's like supposed to say usage and spelling should be independent of one another given the embedding. So that's kind of what our model wants to do. Fun fact about these little light bulby things, we had written the paper and I was so fucking done with it. This was like rejected 2 times already, and it finally got in somewhere, and I was like, fuck, let's just get this done with. But when I made the slides, I came up with these little light bulb statements and was like, they're kind of cute. And I was like, Jason, look at this little summary I made. Look at these light bulb statements. It's like, nice, yeah, that's a great takeaway. That's a great takeaway. And it's like, I know, right? But, you know, it's the paper's already done, so, you know, we can't go back and edit it, right? Like, we've already decided to ship it. And there was like Yeah, no way. That's not how JSON works. No, we went back and rewrote the paper to make it fit nice and kind of make these things more explicit. And I think that was a good idea. But, poor younger me was very sad to be coming back to this horror project. So yeah, that's a blast from the past. Now we're really almost out of time, which is a shame. I don't know why it took so long. Maybe I shouldn't try to be so funny. So I'm going to really briefly go through this because I think this is another neat takeaway that I really want people to see. This is about gender bias on language models. Now, gender bias is very easy to see in like co-ref systems. If we have like, even though the doctor reassured the nurse, she was worried. Who does she refer to? Could be the doctor, could be the nurse. Both are possible, but current systems prefer nurse. So there's work on this because, gender stereotypes. Word embeddings carry biases. We know this. And in a way, this is not really surprising because, he is a doctor occurs much more often in text than she is a doctor. So one way to fix this that was basically proposed by BLEU et al. In 2018 was to balance the training data. So they're saying we have basically this matrix of sentences that could exist. We have male and female pronoun, and we have this stereotype expression doctor, stereotype expression nurse. And so the training counts reappear as likelihoods under a language model. That makes sense, right? If I train a language model on my text, it should assign higher probability to he is a good doctor and she is a good nurse. If I train a language model on my text, it should assign. The solution then that BLEU et al. Propose is what they call counterfactual data augmentation, which really just means for every sentence with she or he in it, we add the same sentence flipping that pronoun. And now we should get a balanced model. Fun fact, when I presented this last year at ACL, I put this little Uno reverse card in trans colors, and I was like, hello, I'm still in the closet, but hello. I don't think anybody noticed, but CDA says trans rights. Anyway, so this is great for English, and it works beautifully, but it turns out English is not the only language in the world. Who knew? So we can say, like, what if German? So this is what it looks like in German. The same matrix again. And we have er and sie, which mean he and she. So we can flip those, and it's great. We also, however, have like male doctor, female doctor, and male nurse, female nurse. So there are different forms in German. So we need to flip those too. And it gets even worse. The adjective good, it also needs to be changed. So this also needs to be reinflected for gender. So that's really nasty. Well, okay, you might say that's easy enough. Like some of the words have genders. We just flip all of the genders of all of the words, right? That shouldn't be hard. So we have this sentence: the male doctor sits on a chair. Well, the doctor is male, the chair is male. Let's just make them both female. And this doesn't work. The chair is male in German. It's intrinsic gender. It's like Spanish in that way. And so this sentence really doesn't make sense. The female doctor sits on a female chair. No, this is not possible. So how do we do this? How do we decide which words to inflect and which ones not? And so the answer is syntax. So we used cancel grammatical gender, yes, please. The answer is we use dependency parses to check here if we want to flip one of the words, which ones have to change. So if we want to flip doctor from male to female, the things that are connected to it might have to change, which is the, good, and sitting, but the others do not change. And so we do this with a Markov random field. Show of hands, who knows Markov random fields here? Who still knows them? I can't see the hands, I'm sorry. I just wanted to say that. Because it's funny, because like after I presented this, someone came up to me and was like, yeah, MRFs, that's a really, really Hopkins thing to do. And I was like, what? This used to be standard. Where did everyone go? But it works really well for our case. So we have some factors for agreement. That's like a neural net factor. So it's not really an old school MRF. We have something for dampening to really select what we want. And so now if we change doctor to female, it should predict that these things change. We run them through a morphological reinflection tool, and we get this new sentence. The good female doctor sits on a chair. And so now with this, we can again look at bias as measuring, like, how likely is it that we have the good male doctor as opposed to the good female doctor? And we see that this is in Spanish. From the original, bias really goes down. Bias both goes down, however, with just swapping everything and with the MRF. So the picture is better when we look at grammaticality. That is, what is the ratio between the good female doctor? The female, good female, doctor female, and the male, good male, doctor, female. So we really want that to be high, right? We don't want that. And so we can see that if we swap, this ratio tanks. So we have low grammaticality, but the MRF kind of preserves it. So this was very encouraging. We also did it on 3 other languages where the results are really bad. So I'm just going to really quickly skip over them. Well, I shouldn't say really bad. They're okay. There are reductions, but it's not as striking as in Spanish. So we talk most about Spanish. In conclusion, English, blah, 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 harder, old school models work wrong, careful with your training data. But the thing that I liked most about this paper is I'm actually using this right now as an example in a class that I'm teaching to show that bias in our models is not just about data, but there is bias in the algorithms. Very controversial view, I know. You can get canceled on Twitter for saying that by the evil mob, but it's true. In this case, the CDA algorithm as proposed, swapping pronouns, looked like a great solution for English, but it was biased towards English. It was by no means language agnostic. And if I had just done this on German and, maybe tuned a ratio or something, chances are I would have tuned it to basically do nothing because it would have completely destroyed my grammaticality. And so I would have ended up with a very biased German language model because the algorithm was biased, because the thoughts that went into building this tool were biased. So bias is not just in the data. And I think that paper shows that really nicely. That's why I wanted to put it here. Now, since we're already over time, I feel like you said you wanted to stop the recording before questions. This might be a good time for that.